2013 Mechanics Paper Level 3, Question 2. We've got swinging balls around in a circle, vertical circular motion. A ball on the end of a cord of length 1.20 metres is swung in a vertical circle. The mass of the ball is 0.250 kilograms. Ball is in the position shown in the diagram. Its speed is 4 metres per second, 0.00. Acceleration due to gravity on Earth, as usual, 9.81. So calculate the size of the centripetal force acting on the ball at the instant shown in the diagram. Centripetal force, we should write what we've got. We've got the mass. We've got the, I'm going to go straight to the equation. Fc equals mv squared over r. We've got the velocity as that instantaneous 4.00 meters per second. And we have the mass of the ball, so that should just be plugging numbers in to calculate it. B, we have to explain why the ball moves fastest at the bottom of the circle. So let's, you have to consider energy for this point. At the top, you have a mixture of energy stored as gravitational potential and the kinetic energy from the moving ball. But at the bottom, you're going to have just kinetic energy. So the change in height, I think this is quite a cool point actually, so I'll just cover it in here. The change in the height is going to be twice the radius. So that's something you might find useful later on, but well, possibly not. Let's carry on. C, diagram 1, bottom left there, shows the gravitational force acting on the ball at the top and bottom of the swing, assuming the tension, I think I didn't answer that top one properly. Just going back to them, because the bottom of the circle is entirely kinetic energy, all of that energy is in motion, so you can do it calculations to show that if you really wanted to, but because it's entirely kinetic energy, all of that energy is going to motion, so it'll have the highest velocity that it can. I'm not sure that I explained that, but carrying on. C. So assuming the tension force is non-zero at all points, draw vectors to show the relative sizes of tension forces at the top and at the bottom. So at the bottom, what we have to remember is that there is always that centripetal force required to maintain the circular motion. So at the top there's centripetal force, which comes from the force due to gravity, and also we've got the tension force added into there. But what have we got? There's two diagrams. So diagram 1 showing the gravitational force on the ball at the top and bottom. Okay, I see. So at the bottom you're going to have a greater tension force in that direction towards the centre, but it has to be larger than when it's at the top of the curve. Otherwise you're not providing enough centripetal force to maintain that motion at that velocity. I'm not certain that the velocity is constant. It shouldn't be in this case anyway, because the earlier example was talking about how the kinetic energy has maximum at the bottom, so the velocity must be greater. You could also go back to your formula, bearing that in mind, mv squared over r. If you have a greater velocity, then you're going to have a greater centripetal force. So that tension force at the bottom will have to be larger than both the sum of the gravitational force and the tension force at the top. If you're going at a minimum velocity, and there is a question about this later on, minimum velocity at the top, your tension force will be 0 and your centripetal force comes entirely from the force due to gravity. Anyway, carrying on. Question 2. Using the same scale, so that's a clue about the size of your forces, you have to draw the centripetal force on diagram 2 at these two positions. Okay, I've just described all of that, but you should have quite a good size centripetal force there compared to there. I haven't done the same scale, it's very difficult to do in these videos, but let's try and match it up. Your tension force will be very small here, and then your tension force on this one would have to be higher than it is over here. So that has to be higher because you're taking away that force due to gravity as well to bring it down to that level. Cool. Hope that's okay. It's the end of the day and I'm a wee bit tired, but I'm trying to get some information out there to help you level 3 students. Anyway, D, show that the minimum speed the ball must have during its circular motion is 3.43 metres per second at the top. So this is minimum speed. Minimum speed is when the centripetal force is entirely the force due to gravity at the top. So at the top, when your kinetic energy is minimum, your velocity will be minimum. So if we look at mv squared over r with the minimum velocity, your centripetal force does have to be minimum, and that's going to be the force due to gravity. You can do your mv squared over r equaling mg. You can cancel out your masses, and then you can find out that velocity by doing gr square root. And you probably used that enough that you could just about memorise that final form of it. G is 9.81, radius is given as 1.20, plug the numbers in, you get your 3.43. In terms of explaining your answer, it's really just explaining why the centripetal force is the force due to gravity, and that's again because for the minimum speed, you'll have no tension force, and that because the tension force adds to the force due to gravity, giving you a higher centripetal force, increasing your velocity. So that's why you have to have no tension force. E, the ball drops to its minimum speed of 3.43 is at the top of the circle. Using conservation of energy, so that's a big clue, show that the angle at which the tangential speed of the ball is 4.00 metres per second is there. So, if we're looking at this purely from a mathematical point of view, you could make a right-angled triangle. I'll just indicate with the little red pointer thingy out of that radial distance. You've got that horizontal distance there, that vertical distance. So the horizontal and vertical give you the right angle, and we just need to know that height there. So let me draw that triangle again. We've got, that's the 1.20 metre radius. We've got our right angle here, and we are trying to find theta. And to get to theta, we really need to know this side length here. And if we just continue the side length up to the top of the circle arc, then that little change in height there, plus this distance here, which I'm just going to get my green pen out again. If we're going that distance there, you can see that we can calculate that angle. But the key is we need to know that change in height. And the best way to use change in height, although it tells you very nicely, is to look at the gravitational potential energy at this point and the gravitational potential energy at the top. We'll call it 1 and 2. So that one's pretty easy. We can just do mgh, using h as the radius, although we have to be very careful that we don't use, if we know the maximum speed at the bottom or we know the maximum energy, that we use an h of 2.4 metres because that's the full height. So you would do the 2.4 metres and then you would use that distance there, that height, which would be 2.4 metres minus that change in height. Okay, so anyway, the change in height bit's the easy bit to calculate than the full thing, because if we can find out the gravitational potential energy at both locations, then mass in m and g are still the same, so we can just reduce that. So if we write a little equation, this is going to make it a little bit clearer. If we write E, P, G, 1, so that's at the it's at this location here. EPG1 plus whatever kinetic energy it has at that point must equal EPG2, we call that kinetic energy 1 as well, plus the kinetic energy at the top 2. So we've got a minimum speed at the top already. That gives us enough information to be able to calculate this because we have the minimum speed at the top, half mv squared using 3.43 meters per second. EPG2, we can do that using the height as well, 2.4 meters, and do that calculation. So everything on the right hand side we know. The kinetic energy at position 1, we're told it's going at 4 meters per second, so we can calculate that. And then we're left with this unknown over here, which is still mgh. We don't know what that height is, but we do know mass, we do know gravity, so we actually know enough using this equation to calculate the height of this point there. Once we've got the height of that point, which is shown in red over the side here, we can just take it away from that 2.4, and then we get that change in height. Or we could even just use that height and subtract 1.2 meters, which is the radial point down the bottom, leaving us with that bit, which will be there, and you can calculate that. Okay, I'm going to leave that up to you to work through though, because it's a little bit more complicated. If you're not sure, go back to the start. The key thing is finding that distance there, and to do that we need to know that height. To know that height we need to look at the comparison of gravitational potential energies and kinetic energies to see the difference in gravitational potential energy. Maybe you can make it a less complicated equation than all of this, but the difference in gravitational potential energy between those two positions will give you the change in height. And there you go.